Right. I think you have go through the last day videos, right? So in the last day, we were discussing about the measuring errors, right? So as I mentioned earlier, the errors can be classified into various types, right? So normally we discuss error as a qualitatively and as well as the quantitatively, right? So under the qualitatively, we discuss there are two types of errors, isn't it? What are they? Systematic errors and random errors, right? So then we discuss what are the examples for the systematic errors as well as the random errors, right? So then we initiated the discussion about the errors as a quantitatively, right? That's mean uh, we try to give some value for the errors, right? So under this quantitative classification, we classified errors into two types, that is fractional errors and the percentage errors, right? So then we discuss what is the meaning of fractional error. So guys, I will recap a small things related with fractional errors, right, and the percentage errors. Right. So if I reveal the equation for fractional error, that should be fractional errors equal to maximum possible error over measured value. This is the equation for fractional error, right? So you know that, guys, the maximum possible error of a measurement is equal to the least count of this measuring instrument, right? So then we can able most probably we consider that fractional error equal to least count over measured value, right? So this is the equation for fractional error, and then we discuss about the percentage error. We discuss about the percentage error. Percentage error is similar as this equation, but the only difference is here we have to consider maximum possible error over measured value. Here we have to consider percentage, so that's we have to multiply it 100. So right, so this is the equation that we discussed on the last day, right? So then at the end of this discussion, I told you a special point, that is, guys, now normally we can able to obtain the percentage value of any kind of measurement, right? So as example, I ask you to find the percentage error when measuring 2 centimeter value, 20 centimeter values by using a meter rule, right? So how should we find the percentage error when when measuring 2 centimeter value in meter rule? That is, now let's find the percentage error relevant for this value, right? So if we use meter ruler, guys, the maximum possible error or the least count of the meter rule. So what it should be? It should be equal to 1 millimeter, isn't it? Then it should be divided from 2 centimeters into 100, right? So in order to convert this centimeter value into millimeter, we have to multiply this value 2 from 10, isn't it? So then it can be mentioned as 1 millimeter over 20 millimeter into 100. So then the percentage error can be obtained as 5%, right? Then in measuring 20 centimeters, the fractional error can be considered as 0.5 centimeters, isn't it? Right. So then So when measuring 2 centimeters using meter rule, the percentage error is equal to 5. Then when measuring 20 centimeter from meter rule, the percentage error is equal to 0.5%, right? So then the theory is, if a obtain reading or measured value to be correct, to be accurate, the percentage error should be equal or lesser than 1. Percentage error should be equal or lesser than 1, right? Then, according to this theory, measuring 2 centimeter value from using a meter ruler, is it accurate method? No, this is incorrect, because the percentage error is greater than 1. So then we consider that, guys, measuring 2 centimeters using a meter rule is a false one, right? And when measuring 20 centimeters from using a meter ruler is accurate one, because it is at this moment the percentage error is lesser than 1. So this can be considered as a accurate measurement, which is if we taken this value from using a meter rule. So right, so this is the just a quick recap on the previous day session, right? So guys, so today onwards, today I'm going to discuss about some important facts regarding the errors. Then let's move on to the measuring instrument part, right? Okay. Now, guys, I will tell you some additional thing, right? So this is for your knowledge, right? So keep in mind those stuff. This is the example. Now I will tell you some 3 examples, which is now if you are asked to make a relationship, then at this moment this theoretical point will be will be support for you, right? Okay, now guys, let's consider this equation. Now let's assume whether this k is a constant, right? Now let's assume that k is a constant. So if someone asks what is the relationship between A and B, what it should be? Now we can able to mention that the relationship between A and B is a direct proportionate, right? Because both of these term is in a nominator in the separate side of this equal sign. Then the relationship is, when A is getting increased, what happened to the B? It should be also increased. This is the relationship between A and B in this kind of equation. On the other hand, when the A is decreased, what happened to the B? B also is getting decreased. So then the relationship between A and B can be considered as a direct proportionation, right? Then on the next type, let's consider this equation A equal K over B. Guys, keep in mind that I'm considering this K as a constant, right? So in this instance, we can able to build up some relationship between A and B. It is considered as a inversely proportionate. That's mean when the A is increased, the opposite happen to the B. That's mean B is decreased. If the A is decreased, what happened to the B? B should be increased. Then in this kind of instance, we can able to consider that when the A is minimum, we can able to consider that B is obtain the maximum, because they having a reciprocal value, right? So according to the first instance, when A obtain the minimum value, B also obtain the minimum value, because these proportionation can be considered as a direct one, right? So in the third example, let's take this kind of instance. Let's call that A, product of A and B is constant, right? So according to this instance, we can able to consider that when the A is increased, what happened to the B? Guys, keep in mind that B having a a reciprocal one. That's when when the A is increased, what happened to the B? It should be decreased. So that's mean the relationship between A and B having a reciprocal one, right? Right. So this proportionation will be helps to support to you when obtaining some relationship between two physical quantities, right? So guys, can you able to just copy those these three instances? Just copy these three instances. Right. Okay. Now let's move back to the this theoretical topic, right? So guys, now we are going to obtain the what is the minimum value that can be taken using a meter ruler accurately, right? Okay. Now just write down this question. I think you have completed the copying these stuff, right? Okay, let's move on to this question, right? Uh, obtain the minimum value. Obtain the minimum value that can be taken accurately. Obtain the minimum value that can be taken accurately by using a meter ruler. By using a meter ruler. Right. Now, just think about that, right? So now we are using meter rule, right? So in a meter ruler, you know that what is the maximum possible error? It should be 1 millimeter, isn't it? Because it is equal to least count, right? So now we are the question is asking that what is the minimum measured value? So this quantity is become minimum. So this quantity is become minimum, right? So at this instance, when the measured value is obtained the minimum, what happened to the percentage error? What happened to the percentage error? Now I think you might get the question which I am asking, right? So now according to this theory, this relationship, this percentage error, let's consider these two physical quantities, that is percentage error and measured value. So percentage error, they are located in besides of the equal sign, and percentage error in the nominator, but the measured value, this quantity is in the denominator. So it is relevant to this instance now. So that's mean A and B, or the percentage error and the measured value having a reciprocal relationship. That's mean when the percentage error is increased, measured value should be decreased, right? So then if the measured value is minimum, percentage error should be maximum, isn't it? So when the measured value is minimum, then obviously percentage error should be maximum, right? So what is the value which can be taken to the maximum percentage error to be the accurate value? To accurate obtain value, to accurate obtain value, we know that maximum percentage error is equal to 1, right? So you should able to obtain, or you should be able to get this point when you are asking this kind of questions, right? Okay, now let's assume that the minimum measured value as x. Then if I substitute the relevant values for this equation, then obviously percentage error should be equal to 1, right? And the maximum possible error should be equal to 1 millimeter. Then let's consider that the minimum value as x into 100. So accordingly, the x should be equal to 100 millimeters, or it can be mentioned as centimeter. It is equal to 10 centimeters. So guys, the 10 centimeter is the minimum value that can be measured accurately using a meter rule, right? So the values which is below the 10 centimeter cannot be measured using meter rule accurately. So that's why we have to go for the other measuring instrument to measure the values which is less than the 10 centimeters, right? So did you get that point? Just raise your hand if you get this point. Right. What about others? Right. Okay, great. Okay, guys, just copy those stuffs. Right. So now we have discussed about the percentage error, right? So then finally we have derived that 10 centimeters is the minimum value that can be measured accurately by using a meter rule, right? Okay, guys, let's move on to the other things which is related with errors, right? Just put a topic as representations of errors. Representation of errors. Representations of errors. Right. Okay. Now let's assume that, let's take this instance, that is let's assume that the distance of this instrument, or the length of this object as simple L, and the maximum possible error when measuring this length as delta L, right? So guys, on the other hand, you know that this maximum possible error is equal to least count of the particular measuring instrument, isn't it? Right. So normally This is the value and this is the possible error in taking this measurement, right? So this measurement can be written as, with considering error, value can be mentioned with considering error as L del plus or minus delta L, right? So guys, this is the way that we normally represent a value, a measurement with considering errors, right? So this is the normal way that we express the value with considering errors, right? We have to mention that this is a possible error or the least count. So it could be plus or minus. So I have told you what is the meaning of this measurement. What is the meaning of this notation? That is, the accurate value is L, but it can be it should having a L minus delta L or L plus delta L, right? So that's mean this length having a range of value. Let's take an example. Let's assume that now I am going to measure a value which is equal to 20 millimeters, right? So let's assume that the length of this object as 20 millimeters. So if I measure this value using a meter ruler, then you know that delta L, or the maximum possible error, maximum possible error of that measurement is 1 millimeter, because I'm taking this measurement using a meter rule. So that's why maximum possible error is equal to 1 millimeter. So this value, this length can be expressed by considering error as 20 plus or minus 1 millimeter. So that's mean, guys, this value can be 20 minus 1. That's mean 19 millimeter. Or it can be 20 millimeter. Or 20 plus 1. That's mean 21 millimeter. So out of these three values, this length can be obtained. Right? So this is the meaning of this sentence. Right? Okay. Now, by considering this value, we can able to derive the fractional error as well as the percentage error, right? Okay. Now let's consider this one, guys. Now if you are given this kind of expression or notation, that's mean this is the measured value. That's the L. But if we consider the error, that the accurate value should be L plus or minus delta L, right? So delta L mean maximum possible error or the least count, right? Okay. Now if we obtain the fractional error relevant to this measurement, fractional error relevant to this measurement. Now fractional error mean maximum possible error over measured value. This is the fractional error, guys, right? If we taken the percentage error can be expressed as delta L over L into 100. That's it. That is the way that we express the fractional error and the percentage error. Guys, you have to be familiar with this kind of expressions, right? Because normally these are very vulnerable to get at the exams, right? Okay. Now, if we apply this fractional error and the percentage error for this example, the fractional error can be expressed as the 1 millimeter over what is the obtained value? 20 millimeter. This is the fractional error, so it should be 1 over 20. The percentage error is equal to 1 millimeter over 20 millimeter into 100, right? So this is the way that we can able to express the fractional error and the percentage error in a given instance, right? Okay, guys, raise your hand if you clear this enough. Right. Okay. Guys, just copy these things in your textbook. Right. Great. Right. So let's take another example. Let's take another example. Right. So let's take this sheet, right? So the area of this sheet, the obtained area of this sheet, let's consider it as 200 square millimeters, right? And the error, I'm represent area as A, and the percentage, the maximum possible error when measuring when measuring area. Let's assume that let's assume as 2 square millimeters, right? So then we can able to give the accurate value, in considering error can be expressed as 200 plus or minus 2 square millimeters, right? So this is the normal way that we express the accurate value with considering errors, right? But normally we are mentioning 200, right? So this is the normal way. But if we do consider the error, we have to express this value according to this notation, right? So keep in mind that. So if someone asks to obtain the percentage error and the fractional error at this instance, the theory is you know that fractional error can be written as maximum possible error, that is 2 over obtained value is 200. So this is the answer, 1 over 100, right? So this is the answer. And if someone asks to percentage error, it should be considered that what is the maximum percentage, or what is the maximum possible error or the least count? It should be equal to 2 over measured value is 200 into 100. Right. So this is the way that we express the fractional error and the percentage error by looking at this measured value and the error. Right. Okay. Is it clear, guys? Okay. Right. So just copy these examples to this one as well as the other one. Now just put the topic as applications of mathematical functions, applications of applications of errors in different mathematical functions. Applications of errors in different mathematical functions. Applications of errors in different mathematical functions. Right. So as I told you, this one is one of the important thing, right? So try to get this everything clearly, right? Okay, guys, let's assume that now. Let's assume that I'm taking a measurement. Let's call it as A. I'm considering this measurement as A, and the maximum possible error or the least count of this measurement I'm considering as delta A, right? And I'm taking another examples, that is I'm taking a value of capital B by using another measuring instrument, and let's call the maximum possible error as delta B. Guys, this delta represent whether it is a very small value, right? That's the meaning of putting delta, right? To emphasize whether it is a small value, right? Okay. Now, we can able to express the percentage error at this instant or of this measurement, percentage error of this measurement as delta A over A into 100, right? So if we consider the percentage error at this instance, percentage error can be expressed as delta B over measured value is B into 100, right? Okay, now keep in mind that, guys, the errors now in any mathematical functions, errors is always is at each other, right? Okay, now just write this sentence under the topic, right? Error is always at each other. Error is always at each other's at any mathematical functions. Right. What is the sentence? Errors are at each other at any mathematical functions. Okay, guys, let's move on to the theoretical things. Okay, now I am considering this percentage error measuring A, percentage error in measuring A. This is the expression, right? So this is the percentage error in measuring B, right? So I am considering that this whole term as X, right? For the practical purposes, right? And I am considering this whole term as Y for the practical purposes, right? For the simplicity, right? Okay. Now let's come to the topic. Guys, let's assume that there's a term called P. There's there's another parameter which is called P, and P can be obtained by adding A plus B. Now let's assume that if someone asks to add these two at each other, then it can be represented as A plus B, no, right? So let's assume that percentage error in measuring P. So as I mentioned earlier, when considering errors, it is always at each other, right? So now you know that, guys, P is obtained by adding A plus B. So then, if you ask to obtain the percentage error in measuring P, can be expressed as what is the percentage error which can happen when measuring A? This is it, isn't it? It is delta A over capital A into 100. This is the percentage error which is happen when measuring A. It should be at 2 percentage error when measuring B. That is delta B over capital B into 100. Right? So it's on the other hand, it can be represented as x plus y. Right? Okay. I'm taking another example, that is, now at this point you can able to get the meaning of these errors, right? So let's assume that, guys, there's a another parameter which is called as Q. Q can be obtained by subtracting P from A, right? So let's assume that percentage error in measuring Q. Now, when we come to the percentage error when measuring Q, Q is obtaining by considering difference between A and B, right? Even now, we know that when measuring A, this is the percentage error. When measuring B, this is the percentage error, right? So, in any instance, I mentioned that errors is always at each other, right? So then, even there's a subtraction between A and B, the errors always should be at each other. Then this can be represented as this is the error measuring A, that is delta A over A into 100, plus this is the error when measuring B. Errors is always at each other. That's the theory. Right. See? Even there's a subtraction, errors, when considering errors, it always should be at each other, right? Okay. On the other hand, we can able to mention this percentage error in measuring P. Let's assume that P is the measured value. Let's assume that maximum possible error of P, maximum possible error in measuring P can be expressed as delta P. Then percentage error of P, percentage error in measuring P can be also expressed as delta P over P into 100. So this value is equal to sum of these two, isn't it? Right. This one also can be expressed as delta Q over Q into 100, right? So these are known. Now, even the expressions is apparently are too long. The meaning of these terms are very simple, right? Keep in mind that errors is always at each other, right? Okay. Now just copy those stuffs. First of all, just copy these two things, and I'm considering 6 examples, right? So out of 2 out of 6, I have mentioned in the board. I will explain the others also, right? Okay, just complete these things. And keep in mind that this is the way that we can able to express percentage error in measuring P, right? This is the way of expressing this this sentence, right? So it is equal to x plus y. These are just expressions, right? Just representations of these errors. Nothing else, right? Okay, just copy those stuff. Hurry up, guys. Right? Right. So now we have discussed two instances. Let's take another one. So guys, this is the third example, right? Let's assume that there's another quantity as Z, right? So Z can be obtained by obtaining product of A and B, right? So X is a particular physical quantity and Z can be obtained by considering product of A and B. Okay, right. So percentage error in measuring P. So guys, let's assume that the maximum possible error in measuring P as delta P. So the percentage error in measuring P can be represented as delta P over P into 100, right? So as I mentioned earlier, even the any mathematical function is there, error is always at each other, right? So then there's a multiplied by b, even though when we come to the fractional error or percentage error, the error is always at each other, right? So then percentage error in measuring, sorry, let's consider that the measured value as Z. Let's consider it as delta x, right? Delta Z, then delta Z over Z. This is the representation of percentage error in measuring Z, right? Okay. Now, even the when measuring percentage error in measuring Z is always can be expressed as delta A over capital A into 100. So this is the percentage error when measuring A. It should be plus percentage error of B when measuring B, right? So this can be expressed as x plus y. See, because now I am considering this expression as x, so that's why I am considering x plus y, right? So in this instance, we can also written this as x plus y. Instead of these two, I am using x and y, right? Okay. Then let's take another example. That is, let's consider it as the fourth one. Okay. Now let's assume that a parameter of physical quantity of R can be obtained by dividing A from B. Even there's a divide, the percentage error in measuring R, percentage error in measuring R can be expressed as, even there's a division, the error is always at each other. So the percentage error when measuring A can be expressed as delta A over A into 100 plus delta B over capital B into 100, right? So this can be represented. So let's assume that the maximum possible error when measuring R as delta R. So then delta R over capital R into 100. Then it can be represented as delta A over capital A right. So on the other hand, I can able to use x and y instead of these two, right? Okay, just write it down. Is it clear, Lamai? Is it clear for you? Raise your hand if it is. Right. So now we have discussed about some examples which is relevant with A and B. Okay. Let's take another one. Okay, this is the fifth example, right? Let's take this one as, let's call it as H, right? So H can be obtained by considering, or the if I mention it as an equation, H is a physical quantity. H can be obtained by A square, right? H is a physical quantity. H can be obtained by considering A square, right? Okay. Now let's assume that. Now here, guys, you know that A square mean A should be multiplied by A, no? Right. So the same thing, percentage error in measuring H. In measuring H can be obtained as, now A squared mean A into A, no? Right. So that even though there's a multiplication, the errors is always at each other. Then this can be represented as delta A over A into, so guys, I'm considering this one as capital A squared, right? So capital A squared mean A into A, no? Right. 100 plus delta A over A into 100. So even though, so this can be represented as x plus x, isn't it? Or on the other hand, guys, this one can be expressed as 2 delta A over A into 100, isn't it? So this can be represented as this equation. Or on the other hand, this can be mentioned as, now this equal, now this is x plus x, no? This represents the x, and this one also is represent the x. So that's mean x plus x. On the other hand, x can be considered as x plus x. So that's mean it is equal to 2x, isn't it? Right. So now I am going to mention you a theoretical things, that is, if you are given an expression with including powers, right? If there's a expression which is including powers or indices, then the error of this particular measurement should be multiplied by from this power. Now, in this instance, the power is equal to 2, isn't it? So the error should be multiplied by 2. That's it. Okay. Now let's take another example. I'll write it down here. This is just an example, right? Okay. Let's assume that there's a physical quantity called as A, G. So G can be obtained by considering B cube, right? So the percentage error in measuring G, percentage error in measuring G can be directly obtained by, now B cube mean B minus B multiplied by B, no? But even though, as I mentioned earlier, if there's a power, then we can able to multiply by this percentage error of the B from 3, right? So this can be expressed in another, or I have considered that this whole term as y, so this can be mentioned as delta y. See, these are very simple things, right? This is the first example. Let's call it example A. And if I consider another one, I'm considering another example. Let's call it, there's a physical quantity which can be obtained by root A. Now K, there's a physical quantity K, and K can be obtained by, let's consider by considering root A, right? So now guys, what is the power which is expressed with this root sign? It's obviously half power, isn't it? A square can be expressed as a half. So then, now if you are willing to obtain the percentage error of measuring K, so I am writing this one. So this is equal to, what is the power? What is half? It should be multiplied by this percentage error of A. This is the normal thing. Or this can be expressed as half x. Right? Okay. Guys, let's move on to the another example. This is the sixth one. Let's assume that there's a physical called, let's call it as G, right? So G can be obtained by A cube over B. So at this instance, how should we obtain the percentage error of B, of G? And now I'm directly writing this percentage error of G as, this is the percentage error of G, right? So this can be obtained by, now here we have to consider A squared also B, right? So you know that now directly we can be able to obtain the error which can be have occurred during measuring A squared. That is 2 multiplied by 2 A delta OA over A into 100 plus delta B over capital B into 100. On the other hand, this can be written as 2x plus y. Right? So this is the normal way that we expressing these kind of things, right? Guys, I'm mentioning by putting this term as the percentage error of G. This is the way I represent the percentage error of measuring G, right? So is it clear, guys? Is it clear? Guys, let's move on to the a question which is related with this theoretical points, right? Okay, just write down this question. Just write down this question. A student measure the a student measure the thickness of a student measure the thickness of a student measure the thickness of a cardboard sheet. Measure the thickness of a cardboard sheet by using a vernier caliper, right? A student measured a thickness of a cardboard sheet by using a vernier caliper. The obtained value is equal to 0.5 millimeters. the thickness of this cardboard sheet is equal to 0.5 millimeters. Right? First one, Roman number 1. Find the percentage error. Find the percentage error. Find the percentage error of the above measurement. Find the percentage error of the above measurement. Within brackets, just put it as assume that in the within bracket, assume that least count of vernier caliper is 0.1 millimeter. This is the least count of the vernier caliper. Least count is equal to 0.1 millimeter. Right. That is the first question, guys. Just draw this diagram in your textbook. Just draw this diagram. Then you have an idea what's the meaning of this, what is the thing which is mentioned in this question, right? Right. So the second question in the second Roman number, instead of measuring thickness of a single sheet, instead of measuring thickness of a single sheet, he kept 10 sheets according to the diagram. 10 sheets according to the diagram. Right. Simple A part. Find the value of H dash. Find the value of H dash. Now he has kept 10 sheets according to this diagram. Now you have to find the H dash, right? So in this instance, there are 10 sheets which is kept according to this diagram, right? Simple B, find the percentage error. Find the percentage error. Find the percentage error in measuring H dash. In measuring H dash. In measuring H dash. Right. Third question. To obtain accurate value for the thickness, within bracket, percentage error is equal to 1%. Percentage error equal to 1%. Right. Just close the bracket. Find the number of sheets find the number of sheets. Let's assume that it is as capital N. Find the number of sheets that should be kept according to the diagram. According to the diagram. Okay, guys. Now I will give you some few minutes to complete this to answer to this question, right? Okay. Just answer the question as soon as possible. Guys, just copy those diagram when obtaining the answers, right? Because then you can able to obtain an idea what is the way of keeping the sheets, right? Now guys, keep in mind that now when we obtain the this every the thickness value is taken by using a vernier caliper, right? So in this instance, we measure the thickness of the single sheet. At this instance, we measure the thickness of 10 sheets at once, right? So instead of measuring the thickness of a single sheet, we kept 10 sheets according to the diagram and measure the thickness at once, right? So keep in mind that okay, right. So in the first question, I am asking you find the percentage error when obtaining this measurement, right? So now you know that, guys, when obtaining measurement, the percentage error equal to maximum possible error, or the least count equal to that is 0.1 millimeter divided from, so what is the obtained value? That it should be 0.5 millimeters, isn't it? 0.5 millimeters, and it should be multiplied by 100. So then the answer should be the 20%. So that's mean this is the a completely wrong value, right? Because the percentage error has increased up to 20. So that is, it is completely a wrong one. However, that's fine, right? Because you don't need to worry about the accuracy of the equation of the value. Just go through the answers, right? Okay. So the answer for the first one should be equal to 20%, right? Okay. Let's come to the second one. So in this instance, we have kept 10 sheets according to this diagram. So that's mean the one sheet having a 0.5 millimeter thickness. So that's mean if we kept 10 sheets, so that's mean H dash is equal to 0.5 millimeters into 10. So that's mean the answer should be the 5 millimeters, right? Okay. Now when we obtaining the percentage error at this instance, most probably most of the students made mistake when substituting the values for maximum possible error. Now this is the equation which is used to obtain the percentage error, isn't it? So guys, if we substitute the values for this equation for this instance, now measured value is equal to 5 millimeters, right? So this is the measured value and it should be multiplied by 100. And when you substitute in the maximum possible error or the least count of this measuring instrument, do we need to answer it as what is the least count? 0.1. Should we substitute it as 0.1 millimeter, or should we substitute it as 0.1 into 10 millimeters? So what is the correct substitution for the maximum possible error? Is it A or is it B? Just leave a comment, guys, mentioning what is the correct substitution for the maximum possible error at this instance. So does it 0.1 millimeter or it should be 0.1 multiplied by 10? What is the answer? A or B? Just leave a comment. Right. Okay. Right. So this is the crucial point in this question. Now, even we kept 10 sheets according to the diagram, we measure the thickness by using vernier caliper at once, right? So that's why maximum possible error at this instance also is equal to 0.1 millimeter. That's it. Because we know, even we measured the thickness of a 10 sheets, we use the same vernier caliper at this instance also. So that's why we have to substitute it as 0.1 millimeter, right? You don't need to worry, you don't need to multiply by this value from 10, right? Okay, so then correct value should be equal to 2%, right? Okay. Now, this is the crucial point in this question, right? Because most probably there's a tendency to substitute 0.1 into 10, right? Because we are measuring 10 sheets, but it is completely false thing. Keep in mind that even we kept 1,000 sheets, the maximum possible error should be equal to just the least count. You don't need to multiply the least count from the number of sheets, right? Okay, let's move on to the third question. Now, in this instance, when we kept 10 sheets, the percentage error is equal to 2, right? So now the question is asking how many sheets that need to be kept to obtain the percentage error to present 1%, isn't it? Okay. Now let's substitute. Now let's assume that if we kept capital N number of sheets accordingly, then the thickness can be obtained by the thickness of a one single sheet is 0.5 and it should be multiplied by n, isn't it? To obtain the thickness of the thickness of the 10 sheet or the measured value, we multiply the thickness of a single sheet from 10, isn't it? So likewise, in order to get this the thickness of this instance, at this instance, we have to multiply the thickness of a single sheet from the number of sheets. Okay, then percentage error should be equal to 1. Now, as I mentioned earlier, even we kept thousands of sheets, the maximum possible error is directly equal to least count of the instrument. So that should be substituted as 0.1 millimeter. The measured value should be equal to 0.5 millimeter into n multiplied by 100. Then n can be obtained as 20 sheets, right? So this is the way that we obtain the answer for this kind of questions, right? Now this is the theoretical things which is relevant with errors, right? So now we have completed the discussion of the errors. Now let's move on to the next topic, right? So up to now we have discussed the units, dimensions, and measuring errors. So from now onwards, we are going to discuss about the measuring instrument, right? Okay, just put a topic as measuring instruments, right? So this is the uh, um, a one of the important topic in this first lesson, right? Right. So now under this lesson, we have discussed 4 measuring instruments, right? First one is vernier caliper. Vernier caliper. Second one is micrometer screw gauge. Micrometer screw gauge. Third one is sperometer. Sperometer. Fourth one is traveling microscope. Right. So these are the main 4 instruments which we need to discuss very clearly in this first lesson, right? But additionally, we have to discuss about the triple beam balance as well as the stopwatch. But these are very small things, right? So just put these 4 measuring instruments. So these are the things that you need to discuss under this lesson, right? Just put these 4 measuring instruments. Right. Okay, guys. So before move on to discuss the vernier caliper, first of all, let's find out what is the meaning of vernier concept. Guys, this all of these measuring instrument is based on a particular concept, right? As example, vernier caliper and a traveling microscope is based on vernier concept, right? So both these two measuring instrument is based on the vernier concept, and these two is based on the screw principle, right? So before going to start the discussion about this measuring instrument, it's better to have an idea about this concept, vernier concept and the screw principle, right? Okay, just first of all, just put the topic as vernier concept. Vernier concept. Just put the topic as vernier concept. Right. So now this vernier concept or vernier caliper is introduced by a scientist called Pierre Vernier. This concept, this vernier concept or the vernier caliper is introduced by the scientist called Pierre Vernier, right? And this is the thing that he mentioned about the vernier scale, right? So first of all, I'm give you some idea about the main scale, right? So now if you are able to get the meter rule, just take it out. In the calibrations of the meter ruler, right? So this is the normal calibration of the meter rule, right? So guys, let's assume that this scale, which is mentioned in the meter ruler as the main scale, right? So this is the main scale. Now, according to this diagram, this is the 0 centimeter division, and this is the 1 centimeter divisions, right? So from this 1 centimeter distance, or this 1 centimeter length, is further divided into 10 divisions, isn't it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's why if we consider these two, if I consider the distance of these two division is considered as the uh, division of a main scale, right? This can be considered as the division of a main scale. On the other hand, division of a main scale can be considered as the length of the adjacent divisions of main scale. So I'm using MS to represent the main scale, right? Okay, now according to this theory, division of a main scale or length of the adjacent divisions of main scale can be obtained by it is considering 1 centimeter and it is divided into 10. So that's why the division of a main scale can be expressed as 0.1 centimeter, or it can be expressed as 1 millimeter, right? So this is the value of division of a main scale, right? Okay, so this is the normal thing which is appeared in the in a meter rule, right? So this scientist, that is Vernier, he introduced another scale that is called as a Vernier scale, right? To obtain the Vernier scale, what he did is he consider some particular distance of a main scale. Now, according to the simplest Vernier scale, this is the simplest Vernier scale. He selected 9 millimeter of the main scale. He Vernier selected. The scientist selected 9 millimeter distance of the main scale, and this 9 millimeter distance he further divided into 10 divisions. Right. And he expressed as the scale as the Vernier scale. He introduced this scale as Vernier scale. Right. So the division of the division of the Vernier scale, so that it is represented as y, right? So this is the division of a Vernier scale. Division of a Vernier scale. Division of a Vernier scale, or it can be expressed as length of two adjacent. Two adjacent divisions of Vernier scale. I'm using VS to represent the Vernier scale, right? So the division of a Vernier scale can be obtained by considered length of the main scale divided by number of vernier divisions. Guys, you have to be very familiar with these equations, right? So this is the way that we obtain the division of a vernier scale, that is considered length of main scale is divided by number of divisions in the vernier scale, number of vernier divisions. Now, according to this given diagram, he selected 9 millimeters, right? So the considered length of main scale is equal to 9 millimeter, and this 9 millimeter is further divided into 10 divisions, right? And this 10 divisions can be considered as the vernier divisions. So then the vernier division should be equal to 10. So hence the distance of the vernier division or division of a vernier scale is equal to 0.9 millimeter, right? So this is the normal way that we obtain produce the vernier scale, right? Selected, first we have to select a particular distance of the main scale, and it is divided into number of vernier divisions. Then we can able to define this newly made scale as the vernier scale, right? Okay. Now, guys, I will tell you another important things which is relevant with considered length of main scale. Normally, they are given the exact value which we selected in the main scale, but sometimes it is not, right? So that's why I'm considering this equation. In any instance, considered length in main scale can be obtained by division of a main scale multiplied by number of main scale division. Right? So you will able to know about what is the meaning of these names, right? What is the meaning of these terms in when doing the questions, right? So up to now, just keep in mind those stuff, right? Okay, guys. So just copy those stuffs in your textbook. Right, guys. So this is the way that we obtain the division of a main scale and the division of a vernier scale, right? Okay. Then let's put the topic as least count, right? As least count. Right. Guys, least count mean the minimum value that can be measured using measuring instrument, right? Because now most probably you might have some issue. Now in one instance I mentioned that what is the measurement that can be obtained accurately using the meter rule. So at that instance I mentioned, guys, and I want to impress that the minimum measurement that can be measured accurately, right? So in a meter ruler, the minimum measurement that can be measured accurately in the meter ruler is 10 centimeters, right? On the other hand, the least count or the minimum value that can be measured using meter ruler is 1 millimeter. So they are apparently looks like same, but even though that 10 centimeter represent that the measurement, the minimum measurement that can be measured accurately, right? So that so these are two different things, but apparently they looks familiar, isn't it? Okay, now least count. Let's write down this one. Least count. Least count is the minimum. Is the minimum value that can be taken that can be the minimum value that can be measured using measuring instrument. Least count is the minimum measurement or minimum value that can be measured using measuring instrument, right? So this is the meaning of the least count, right? This is the meaning of the least count. Minimum value that can be measured using using a measuring instrument. That's the meaning of least count, right? Okay. Now, guys, least count can be obtained in two different ways. In in measuring instrument which is used Vernier concept, right? So this method is only applicable to the measuring instrument which is used Vernier's concept, right? So then least count can be obtained by division of main scale, subtract division of Vernier scale. This is a one certain type that we can able to obtain the least count, right? So according to this given diagram or given example, division of a main scale is equal to 1 millimeter and division of a Vernier scale is equal to 0.9 millimeter, isn't it? 0.9 millimeter. Hence, least count should be equal to 0.1 millimeter. That's the answer, right? Okay, so this is the first way that we are able to obtain the least count. And there's another way, that is least count can be obtained division of a main scale, dividing the number of Vernier divisions. Now, according to this given example, division of a main scale is 1 millimeter and number of Vernier divisions, that is 10, isn't it? So the answer is equal to 0.1 millimeter, right? So guys, these are two different types of equation. Apparently, this one is the most easiest way, isn't it? Right. So this is the easiest way, but you definitely have the both systems, right? Okay, just copy these things